Hello, in this video I'm going to start going through some oscillations questions. So this is going to have lots of stuff on simple harmonic motion. Just going to go through them fairly quickly. We've got two standard conditions concerning the acceleration of an oscillating object that must apply for simple harmonic motion. Right, so two things. Seeing as we're talking about acceleration, then we're going to say something about the magnitude and something about the direction. And then that's going to cover what we need for this vector that is acceleration. So the acceleration has to be proportional to the displacement. So we have to say what is displacement from. So that's displacement from an equilibrium position. And then in terms of direction, so we then need to say and A is directed towards the equilibrium position. So that's our two statements there. Now we're onto a graph which is showing potential energy against displacement for a simple harmonic oscillator. On that graph, sketch graphs to show the variation of kinetic energy and total energy with displacement. Right, I'm actually going to start with the second one because, well, that's a bit easier. We know it's going to have to be constant. We know that at the maximum potential energy, we've got no kinetic energy. So the most we're going to get is this 18 millijoules that we got up here. So I'm going to try and draw a horizontal line on that to show that it's constant. A little bit wonky, but not too bad. So that's a horizontal line going through 18 here. That's our graph T. The kinetic energy, when you add it to the potential energy, it's always got to add up to this 18. So when we got the maximum potential energy, we got nothing for kinetic at the amplitudes, and then the opposite of that in the middle, that must be where we got maximum kinetic energy. And then we just need to join this up into the upside down version of the curve that's already there. Again, a little bit wonky, but you get the idea. That's our curve K. And then if you add those two together, you get the red one at the top. So that's pretty straightforward, standard stuff. And now we need to use these graphs to determine the amplitude of the oscillation. So that's the maximum displacement, which you just read straight off, 0.04 meters. The maximum speed. So maximum speed, what I've given us here, that's going to be, we've got maximum kinetic energy. So our half mv squared is going to be equal to this 18 times 10 to the minus 3 joules that we've got there. So they've given us the mass here of 0.12. So v squared is going to be 18 times 10 to the minus 3 divided by 6 times 10 to the minus 2. So that is 0.3. So we just need to square root that, sorry. And then we got V is 0.5477, so 55 meters per second to two significant figures. Now we need to get the frequency of the oscillation, so a little bit more involved. We went through all this on the previous discussion videos on how simple harmonic motion works, and you may recall from that we found that the V max is equal to omega A, where omega is the angular frequency. We just worked out V max here. So what are we trying to get the frequency? So that is 2 pi f times A. So f is V max divided by 2 pi A. Our V max was, so we've got, let's put that back in again to get a more accurate number. Divide that by 2, divide that by pi, and then what we're dividing by A, which is 0.04. It's going to be just over 2 then, so we got 2.18, which is 2.2 hertz, again to two significant figures. Right, I've used up all of the sheet again already, so on to the last bit. Hopefully we don't have too much to say. Resonance can be useful or a problem. Describe one example where resonance has a useful application and one example where resonance is a problem or a nuisance. For each example, identify what is oscillating and what causes these oscillations. Right, there's loads of things you can pick out on these. So something that's useful, you've got things, I always go for the musical instrument one. But you can have things like MRI scanners. I mean, resonance is in the word, in the acronym there for that. You've got microwaves. Yeah, you've got, well, even pushing someone on a swing. But I'm gonna stick with a musical instrument one. So let's go for a trumpet. So you'd want to say the trumpet. So you've identified what it is, and then you'll say. So what do we have to say? We have to say what is oscillating and what causes it. So it's the air in the trumpet that's oscillating, and it's the lip vibration of the person who's playing the trumpet that's causing the air to then start oscillating. So you just need to join those bits into a sentence. And then for something that causes a problem, yeah, I mean, you've got lots of stuff. You've got, buses and cars and things. You really notice it on buses when they start resonating, the whole thing starts shaking like crazy. You've got washing machines jumping around all over the place. I'm going to go for the bridge one because we love watching Tacoma Narrows Bridge. So we'll say the bridge, and that is the bridge that is oscillating. So that is the thing that's oscillating, and it is the wind in the case of the Tacoma Bridge, or when you had the one, was it the Millennium Bridge in London, which is quite a long time ago now, and they had to close that down because everyone was walking in step, and it was the pedestrians, it was the people who were walking on it. And when everyone started walking in step, and then the bridge started swaying around. Yeah, the wobbly bridge or whatever they used to call it. So they had to put dampers on it in order to stop that from happening. So there you go. There's the examples on good and bad of resonance. Next up, we've got the classic, the oscillating spring. We've got slotted masses suspended from a spring. Spring is attached to a fixed support at the upper end. Okay, when the masses are pulled down, short distance from the equilibrium position and released, they oscillate vertically with simple harmonic motion. Frequency F of these oscillations depends on the masses. Two students make different predictions about the relationship between F and M. One suggests that F is proportional to 1 over M, and the other one says it's proportional to 1 over the square root of M. Describe how you would test experimentally which prediction is correct. Include in your answer the measurements you would take and how you would use these measurements to test each prediction. Also, discuss ways of making the test as reliable as possible. All right, well, there's not much we have to actually measure in all of this. We need to have something to do with the mass, which we can measure just at the beginning. So, thinking of our tabular approach of what we'd draw up if we were doing the experiment, we'd have mass, we'd have, we want to have frequency at the end, the frequency of oscillation. So we're going to want to measure time, because that's how we're going to get our frequency. We need to have a clock somewhere. We don't need anything else in this. So we're going to start off by saying that we will measure mass using, what are these, are the slotted masses? Yeah, measure masses in kilograms using scales. Then we will measure time of oscillation using using a stopwatch. So it's the same old approach we have on all of these things. You could say that we will, for increased accuracy, because they want something in here, they want it to be as reliable as possible. So you can say for increased accuracy, we'll measure time of say 10 oscillations and divide by the number of oscillations and divide to get the time for one oscillation. For time of one oscillation, I'm just writing all this in shorthand, but yeah, turn these into sentences. Then we can calculate frequency, which equals 1 over the time period. So this is the time for one oscillation. T equals 1 oscillation time. So make sure you're clear as to exactly what this is when you're calculating it. And then we can plot a graph of, well, we want to plot two graphs. We'll plot graphs of, so what have they got? F versus 1 over m and f versus 1 over the square root of m. And the correct one is the straight line through the origin. So straight line equals correct answer. So our usual approach to doing experiment questions, quite easy to fill everything up. Say what you're measuring and what you're measuring it with, say what you're calculating and what formula you're using, and then say what graph you're going to plot and what it should look like. And then you've already said 8 things before you've even done the bit about increasing the accuracy by doing multiple measurements. And if you start saying 8, 9, 10 things, you're going to pick up all the marks. So when the masses hanging on the spring are 400 grams in total, they oscillate with an amplitude of 36 millimeters in a period of 1.2 seconds. Calculate the maximum kinetic energy of the masses and the maximum acceleration of the masses. Right, we know Vmax is equal to A omega. So that is, omega is 2 pi over t. So that's A times 2 pi over t. Actually, let's just put the numbers in. So A is 36 times 10 to the minus 3. They've given us that. Then we need to multiply that by 2 pi and divide by t 1.2. Right, so that is going to be, what have we got here? We got a 30 when we put that into this. So we've got 60 divided by 1,000, so 6 over 100, 3 over 50 pi. So 3 pi divided by 50. Then we just need to put in our kinetic energy. So a half times m will be, what's m? 400 grams. So half of that, 0.2, multiplied by v squared, multiplied by 3 pi over 50 all squared. I'm going to have to go to the calculator with that because we've got a pi in it. And that comes out as 7.1 times 10 to the minus 3 joules. So pretty small. Maximum acceleration of the masses. So our A max is equal to, well, A omega squared. So that is going to be, what we got? So yeah, 2 pi over t. So 2 pi over t all squared multiplied by A. Then again, we're just typing it all in with the numbers that they've given, which is coming now at 0.99 meters per second squared. So yeah, not bad calculations, providing you're happy with your Vmax and your Amax. List the different types of energy involved in the oscillations of this mass spring system. Describe the energy changes when the mass moves from the lowest point to the highest point. So the types of energy that we've got the kinetic energy, we've got the gravitational potential energy, and we've got the elastic potential energy in the spring. So we've got all of those. So at the lowest point, so yeah, you're going to write this out in sentences, but let's turn it into a bit of a table first of all. So this will be at the lowest point, this will be at the highest point. Oh, and actually let's put something, we might want to put some more in because we're going to want to say more about the kinetic energy. So let's put the equilibrium point as well. So for kinetic energy, it's 0 at the lowest and the highest, and it's a maximum at the equilibrium point. The GPE is, well, it's going to be at its lowest at the bottom and its highest at the top, and it's just going from one to the other. The EPE is going to be going from its highest at the bottom to its lowest at the top. So that's what is happening with all of those. So yeah, we need to, well, turn this into sentences really. So you're just writing out each one of those rows. So you've got the 3 different types. You can say the kinetic energy goes from 0 at the bottom to a maximum at the equilibrium to 0 at the highest point. GPE just goes from the lowest at the bottom to the highest at the top, and then the converse of that for the elastic potential energy, going from high to low, because it's not extended as much at the highest point as it is at the bottom point. So yeah, relatively straightforward descriptions.